All right, today we are going deep. We're dissecting a master engineering plan, and I mean a real blueprint, for what is essentially the brain of a top-tier Formula Student electric race car. We're talking about the Vehicle Control Unit, or VCU. This is where we're going to break down the strategy that really separates the winners from everyone else on the grid.
You know, we've kind of hit a ceiling with hardware. For years, the game was about shaving off a few grams from the chassis or finding another point of downforce in the aero package. But those gains, they're getting smaller and smaller. Honestly, the top teams are pretty much on par when it comes to the physical car. So the big question I always pose to teams is this: when the hardware plateaus, where do you find your next tenth of a second?
And the answer, the one that's defining this era of racing, is software. The new battleground isn't in the carbon fiber shop, it's being fought in lines of code. We're seeing this massive shift towards what we call control intelligence and the whole concept of the software-defined vehicle. This is where the lap time is hiding now.
And right at the heart of this whole software revolution is one critical component, the Vehicle Control Unit, the VCU. It's the car's central nervous system and its brain, all rolled into one, and it is the single focus of our deep dive today.
So, let's talk architecture. A modern VCU can't just be one giant monolithic processor trying to do everything at once. No way! Just like our own brains have different parts for different jobs, a winning VCU has to be split into a specialized architecture, what we call two distinct domains.
The old way of doing things, it was just flat. Imagine one big, crowded highway, the old CAN bus, where every single signal, from a life-or-death motor command to a simple dashboard update, is stuck in the same traffic jam. It's slow, it's crowded, it's inefficient. The new approach is so much smarter. It creates two separate, dedicated networks, with the VCU acting as this brilliant central gateway, directing traffic between them.
And here's the key takeaway of this new architecture: specialization. You have the powertrain domain. This thing runs on what we call a hard, real-time basis using EtherCAT. That means torque commands are sent with absolute military-grade precision. Delays are not an option. Then you have the body domain. It uses the good old reliable CAN bus for soft real-time stuff like sensor data or what the dashboard is showing. Here, being compatible with lots of devices is way more important than hair-on-fire speed.
Okay, so if the VCU is the brain, then the communication network is the car's nervous system. And for a race car, that nervous system has to be perfect. It has to connect the brain's thoughts to the muscles, the motors, instantly and without fail.
And this is why EtherCAT is such a game changer. It's the absolute superhighway for the powertrain. Its secret is a technique called processing on the fly. The analogy here is perfect. On a normal network, a data packet is like a train that has to pull into every single station to drop off a package. It's slow. With EtherCAT, the train never stops. It just screams through the station at full speed, and the station's hardware literally snatches its specific data right off the moving train. It is unbelievably efficient.
And the result of that efficiency? Well, it's just mind-boggling. We're talking about a synchronization accuracy between all four motors of less than 1 microsecond. That is 1/1,000,000th of a second. It's that level of precision that completely eliminates something called torque steer. You know, that dangerous pulling you feel when you floor it? This keeps the car perfectly balanced and stable, even when you're pulling insane G's in a corner. Now we've got the brain and the super-fast nervous system. So let's talk about how this brain actually thinks. And this, right here, is probably the biggest leap forward, moving away from a system that just reacts to problems to one that actually predicts them and stops them before they even start.
The old way, which is called PID control, is like a rookie driver. It's purely reactive. The car starts to slide, then it tries to correct. The new method, Model Predictive Control, or MPC, well, this is the grand master. It's predictive, it's multi-objective. It understands the physical limits of the car. It's like a chess player, thinking 5 moves ahead to put the car in the perfect position and prevent any problems from ever happening in the first place.
So how does this grandmaster actually think? It's all happening in this incredibly fast, constant loop. First, it uses a complex mathematical model of the car's physics. Second, it uses that model to predict exactly where the car is going to be over the next half second or so. Third, it runs a massive optimization problem to figure out the perfect torque command for each individual wheel to get the best outcome. And finally, it sends that command and then boom, it starts the whole cycle over again. And it does this 100 times every single second.
And here's what that really means in practice. An MPC system doesn't wait for the car to spin out. It sees the conditions, it runs the numbers, and it predicts a potential spin out 200 milliseconds in the future. And it applies a tiny, subtle correction right now to make sure that spin never, ever happens. That's what proactive control is all about. It's almost like magic.
So you put this all together, the new brain, the predictive thinking. What does it actually let you do on the track? What are the VCU's superpowers?
This VCU architecture unlocks a whole suite of incredible performance algorithms. You get adaptive torque vectoring that literally helps steer the car into a corner with the motors. You have side-slip angle limiting, which is like an intelligent safety net that lets the driver push right to the absolute edge of the tires. You get predictive energy management that acts like an onboard race strategist, perfectly doling out battery power. And then there's active thermal control, which sees overheating coming and manages power to stop it before it's initiated.
Let's just zoom in on that endurance race for a second. It's the classic problem, right? You go flat out from the start, you run out of battery, you don't finish. DNF. You go too slow to save energy, you finish, but your score is terrible. The NPC's energy algorithm finds that perfect razor's edge right down the middle, squeezing every last bit of performance out of the battery to get the maximum possible points. It's the key to winning that event.
But listen, all this amazing performance, all these clever algorithms, they mean absolutely nothing if the car isn't safe or if it gets disqualified for breaking a rule. The foundation of being fast is, believe it or not, being safe and compliant.
There's an old saying in racing, to finish first, you must first finish. And that's why the VCU isn't just about going fast. It's also the car's ultimate safety guardian, running checks and balances way faster than any human driver ever could.
The VCU is constantly enforcing the rulebook with millisecond precision. Let's say the two accelerator pedal sensors disagree for just a tenth of a second. Boom, power is instantly cut to zero. But my favorite function is what we call the shadow BSPD. See, there's a mandatory hardware safety circuit. The VCU runs a software simulation of that circuit. It can predict when the hardware is about to trip and cause a catastrophic, race-ending shutdown, and it steps in first with a much softer, more controlled power cut. It keeps the car safe without ending its race. It's brilliant.
Now, I know this might all seem like it's happening in this really niche world of student racing, but I promise you, the technology we've just been looking at is directly shaping the future of the car that you will be driving very, very soon. This whole concept of the software-defined vehicle, it's probably the single biggest trend in the entire automotive industry right now. The domain architectures, the predictive control for stability and for efficiency, the idea that a car's capabilities are defined by its code, all of this is coming to the car in your driveway.
And that really leaves us with a pretty fascinating question to think about. As these systems get more and more sophisticated, predicting not just the car's behavior, but the road ahead, maybe even our own intentions, how is that going to change our relationship with the act of driving itself? What's it really going to mean to be in control?